All right, Matt 2, we got lesson 3.1.3, probability models. All right, in a game of pick a tile, players reach into two bags. One of them contains square tiles and one contains circular tiles. So you're not going to get these mixed up. One of them square, one of them circular. The bag with square tiles contains 3 yellow, 1 blue, 2 red. The bag with circular tiles contains 1 yellow and 2 red. In order to win, a player must pick 1 blue square and 1 red circle. It costs $2 to play the game, and winners received a large stuffed animal. Okay, so we got 2 bags that we're going to pick from. So this is 2 separate events. We're going to pick a blue one, that's one event. We're going to pick a circle, not a blue one, a square one, that's one event. We're going to pick a circle, that's a second event. We have 2 separate events happening. So one thing that we can do to look at our probabilities is to do like a tree diagram like we did before. So event number 1 has 3 outcomes actually. This is a square bag. It's got 3 yellow, 1 blue, and 2 red. So there are 1, 2, 3, 4, 5, 6 tiles to pick from. So since we have 6 tiles to pick from, yellow for the square bag is 3 out of 6 times. Blue, you're going to pick that 1 out of 6 times. And red, you're going to pick that 2 out of 6 times. And some of those can reduce, but we'll move on. If you have the circle bag that you're picking from, there are 2 outcomes. We've got a yellow and we've got red. Now in the bag with circles, there's 1 yellow and 2 reds, so there are 3 possible things to pull. One of them's yellow, so you have a 1/3 chance of getting yellow, and 2 of them are red, so you got a 2/3 chance of getting a red. All right, so let's start with pulling a square. So our first thing that's going to happen, our first draw here, our first event, is to pull a square. And 3 things can happen. So we're going to pull up a square, and we can pull a yellow one. We could pull a blue one, or we could pull out a red one. Are they equally likely to happen? No. If we do yellow, we have a 3 in 6 chance, or 1/2 chance. If we do blue, we have a 1/6 chance. And if we do red, we have a 1/3 chance. Okay, that's the first event. We are pulling a square. The second event is we pull from the bag that has circles in it. Now notice these events add up to 100% because you're either going to do a yellow, blue, or red. So once you pull, 2 things can happen. You can get yellow, which is 1/3 of the time for the circles, or you can do red, which is 1/3 of the time. So if I pulled a square that was yellow and then a circle that was yellow, the outcome for that one would be 1/2 times 1/3, which is 1/6. Wait a second. Oh, it's 2/3 for red. So this would be 1/6. 1/2 times 2/3 is 2/6, or 1/3. Now, if we do blue, we're running out of room. Let's just call this yell or Y, and we'll call this one R. So Y and R, just so we have room here. So this is a 1/3 chance here, and this is a 2/3 chance. So we're doing blue first, then yellow. 1/6 times 1/3 is 1/18. And 1/6 times 2/3 is 2/18. And then lastly, we can do red first, and then yellow, and then red second. Again, yellow is 1/3 chance, and red is 2/3 chance. I really don't like the tree diagrams because they get really messy. But whatever. I guess I could have done it nicer, but I didn't. So we're just living with ourselves. I probably should have gone straight down instead of doing it to the side like this. Anyways. All right. 1/3 times 1/3, 1/9. 1/3 times 2/3 is 2/9. All right. So these are our sample space outcomes. This one is yellow, then yellow. This one is yellow, then red. This one is blue, then yellow. This one is blue, then red. This one's red, then yellow. And this one is red, then red. So first one square, second one circle. Let's see, how do we win? In order to win, a player must pick a blue square and a red circle. So blue, then red. Here's how we win right here. A blue, then a red. That is 2 out of 18, or 1/9 of the time. All right, so it looks like to win this, 1 out of 9 times I'm going to pull a blue one first and then a red one second. How would you decide if the game is worth playing? Okay, so this means that I would have to play the game 9 times in order to win once. That is what's probable. It's not definitely going to happen. I could win on the first one. I could never win. It's not likely, but I could keep on drawing and never get the correct order. But the most likely thing to happen is if after playing 9 games, you should win once. So if it costs $2 to play, how would we decide if the game's worth playing? Well, let's look at the stuffed animal. Is the stuffed animal worth $18? Because I have to play 9 times in order to win once. So if I play 9 times, that's going to be $18 I spend. So I would look at that stuffed animal and go, well, is it worth paying $18 for this stuffed animal? If it's like a $2 stuffed animal, then probably not a great game to play. But if you just like pulling tiles, maybe that's just enjoyable enough as it is. Or you just like to gamble, whatever. So you would look at it and say, is the amount of money that you're spending worth the stuffed animal? So is the stuffed animal worth $18? Because that's what the probability says we're going to have to spend in order to get it. In order to get one stuffed animal, I'm going to have to play 9 times. So I'm going to spend $18 to win that stuffed animal. And that's not even guaranteed. That's just what will probably happen. All right, use that same thing, use this same situation to do an area model. I like the area model in this situation better. Like I've said before, I really think that the tree diagram should only be done when there's more than 2 events. So remember we had 2 events, pulling a square, then pulling a circle. Like I like the tree diagram if you're flipping a coin 3 times, because you can't really show flipping a coin 3 times, because this works better with 1 event and then a second event. Whereas a tree diagram, you can keep on making branches as you go. So use the area model, calculate the probabilities, and pick a tile. So same probabilities we had before, 1/2 times 2/3. So this would be 2/6, or 1/3. 1/2 times 1/3, 1/6. 1/3 times 2/3, 2/9. 1/3 times 1/3, 1/9. Probability of blue, 1/6 times 2/3 is 2/18, which is 1/9. And 1/6 times 1/3 is 1/18. All right, there's all of our different probabilities. Which model do you prefer? I prefer the area model. I think it's gets everything together in a nicer display. This one can get messy, but if there were more than 2 events, I'd lean towards the tree diagram. It's kind of up to you. All right, next one. Rimshot McGee That has to be a real person. Has a 70% free throw average. His team is 1 point behind with less than a second left, and Rimshot is at the free throw line with a 1-and-1 free throw shot. Okay, so 1-and-1 means if you make the first one, you can shoot for the second one. If you miss the first one, you don't get a second shot. All right, so find the probability of Rimshot's team winning, ending in a tie, and losing. We're not going to make a tree diagram for this one because I don't think it fits. This one, you have just two outcomes, two events. First shot, second shot. So I'm going to do an area model instead because I think it displays the data better. Again, if you have two events, I really do think that you're going to be better served doing an area model versus a tree diagram. Tree diagrams are when you have more than two events. So we've got two events. He's going to take shot one, and then he's going to take his second shot, shot number two. Those are the two events. All right. Now there are two outcomes with each of those events. Make it or miss it. Those are the only two outcomes that he can do. There's nothing other than make or miss. So he can make the first one, or he can miss the first one. So if he makes the first one, he has a 70% free throw average, so that's 0.7. That means that if he makes 70%, he misses 30%, so that's 0.3. Now on his second shot, he has the same percentage, make, which is 0.7, or miss, which is 0.3. Let's look at our probabilities now. 0.7 times 0.7 is 0.49, so 49%. 0.7 times 0.3 is 0.21, 0.21. 0.3 times 0.3 is 0.09. So 49%, 21%, 21%, 9%. All right, now we have to look at when is he going to win for his team. Remember, they're 1 point behind. He's got a 1-and-1 situation. Well, I can see here that if he wins, that means he makes both of them. So here's where he wins, 49% chance. All right, now let's look at a tie. Now a tie is kind of weird in this one because he's got to make one. But remember, it's a 1-and-1 situation. He's never going to miss the first one and then get a second shot. So the only way to get a tie is over here. He's going to make the first shot, but miss the second one. He just tied. So that's a 21% chance. Because this is a 1-and-1 situation, we have to kind of think through this problem because you might be looking at it and go, what if he misses and then makes it on the second one? Well, if he misses the first one, they're never going to let him make the second one. So in a 1-and-1, if you miss the first one, you're just out. You don't get anything. So the losing situation is these two added together, both of the miss ones. So shot one, miss, would be both of these two situations because he doesn't get a second shot in this situation. So missing is 30%. So if we want to lose, or we don't know if we want to, but if we lose the game, there is going to be a 30% chance of losing the game. So sometimes you have to think through your probabilities and not just blindly read the chart. Write the area model as a product and a sum? Really? They want me to do that? Okay. So as a product, we would do 0.7 plus 0.3 times 0.7 times 0.3. I don't know what the purpose of this is. And then as a sum, 0.49 plus 0.21 plus 0.21 plus 0.09. That might be it. It is! Yay, we finished. All right, good job, guys. All right, so again, yeah, I'm probably pushing you towards doing it a certain way, but I really do think that these area models are a better situation when there are 2 events. Now, if I'm getting 3 events, yeah, I'm going to want to use the tree diagram instead. But, I mean, just look at it. That's just messy. When this one is so clean, it just makes me feel good when it looks pretty like that. All right, that's all I got for you today. Stay tuned for the next one. See you later. Bye-bye.